Why do static analysis tools struggle with dangling pointers? Imagine trying to catch a shadow that keeps shifting and changing shape. That's similar to what static analysis tools face when hunting for dangling pointers. These tools scan code without running it, trying to find bugs like memory issues. But dangling pointers are tricky because they involve memory that has already been freed or invalidated. Static analyzers have a hard time because they can't see what happens during actual program execution. One big challenge is understanding the full life cycle of pointers. In languages like C and C++, programmers manually allocate and free memory. Static analysis needs to follow all possible paths where a pointer might be allocated, used, and freed. But since code can have many branches and conditions, predicting every scenario becomes very complex. This makes it tough to tell if a pointer is still valid or not at a certain point. Another issue is false alarms. Static analysis tools often flag code as unsafe even when it is safe, or they miss real problems. They have to make conservative guesses because they don't have runtime information. For example, if a pointer is freed in one part of the code but still used elsewhere, static analysis might not catch it. This leads to false positives or negatives, which can be confusing for developers. Pointers can point to memory on the stack or the heap. Stack pointers are usually short-lived, tied to a function's execution, so they are easier to analyze. Heap pointers last longer and can be assigned and freed in many different ways. Tracking all these heap pointers and their aliases, when multiple pointers reference the same memory, is very difficult for static tools. They need to analyze indirect assignments and complex data structures, which adds to the challenge. Performance is another factor. To analyze code precisely, tools need to spend more time and resources. But this can slow down the analysis, especially with large code bases. So many tools limit how deep they go into pointer tracking to keep things quick. This trade-off means some dangling pointers might slip through unnoticed. Finally, static analysis cannot see what actually happens during program execution. It lacks real-time information about memory states and pointer values. Because of this, it cannot always determine if a pointer is dangling at runtime. It can only make educated guesses based on the code structure. To improve detection, developers often combine static analysis with runtime checks or dynamic analysis. Using smart pointers or following safe programming practices like nullifying pointers after freeing memory can also help prevent dangling pointers. Understanding these limitations helps programmers interpret static analysis results better and use other debugging methods to catch memory bugs more effectively.